All right, I have no idea whether that's working or not.
Says it's working.
What's that?
Says it's working.
Yeah, I know it's not giving me the display, but we'll assume it's working and that they can see it. So, if not, at least they'll get the audio of it. So, basically what we're going to do today is kind of go through history of codes and some of the green building standards. The whole premise of the course is to look at how we design and build and test buildings for their energy efficiency. But the first thing we really have to do is define what energy efficiency means. And I can tell you that I've been going through this for the better part of 25 years in the building industry, and like so many other things, there's no consensus on what an energy efficient building is. And so part of that, and part of what I hope that we do go through in this class, is that you guys can get an understanding of the building science principles that do impact the energy performance of a building, along with some of the techniques and the materials that we use, how they're integrated together, and then how we actually test and verify that our buildings are energy efficient. And given that basic information of the building science, the techniques and the materials, you can make your own value judgment of what you think is energy efficient, and we'll talk about some of the differences. Currently in the industry, what defines buildings range from building codes, which are, and we'll go through building codes, history of codes, where they're at currently. Building codes were always meant to be sort of the minimum standard. In the industry, when we talk about a house or a building that meets code, it's the bare minimum that you have to do in a building to not break the law. And so that's kind of our first bar in what sets the stage for what we talk about when we define an energy efficient building. Basic history of codes, they started nearly 4,000 years ago basically to guard against catastrophic failure of buildings. We spend now probably 60 to 80% of our time indoors, so it's become imperative that the buildings that we are in are safe, that they're designed so that they're currently probably not all healthy, but at least designed not to make us sick. And that's the impetus of where building codes started from. All right. So right now, these are some of the basic codes that we have, and primarily in United States and North America, the ICC, the International Codes Council, is the preeminent entity that defines what buildings are. So looking through this basic list of codes are pretty extensive. And there's the basic building code, which covers all of our structural, how strong the foundations need to be, everything from just your compressive and shear strengths to, and you don't have to memorize this list of codes. And just for you guys who haven't had classes with me before, I'm not going to give you a whole bunch of memorization stuff. It doesn't really teach you much of anything, but we will work on as we get through this class, and we'll touch on some of these things today. But we will look at really applying some of the things we're learning. And so we're going to take some of these codes, some of the energy requirements of them, and we're going to apply them to buildings. So you're going to have to figure out design loads of buildings and things that do and do not meet code. But we're not going to work on that till the week after next. But so I give you these lists. These slides are all available for you on Moodle, so you can look at these. But I will never give you a test question that says list 18 different international Code Council codes. But this just gives you an idea of some of the different things that are mandated now in the building. And remember, when you talk about a code, these are the minimum requirements. If you don't meet these minimum requirements, the building that you're building does not meet the standard of law. So safety and protection, again, major life safety issues were really the first part of the code. So protecting against fire, protecting against structural collapse, making sure that all of the systems, the mechanical systems, the electrical, the plumbing, are first and foremost not hazardous. The energy codes, the kind of the last piece of it, really didn't come into play until about 20 years ago. Up until that point, there really was nothing, a major requirement that mandated that you used a certain level of insulation and that you used a certain heating system. So in essence, the energy codes are fairly recent, and they've been evolving pretty rapidly since the inception, and we'll go over a little bit more about how the energy codes came through. Basic code development starts with assembly of a large consensus group, and I'll give you some examples for the energy code. When the International Code Council finally decided they were going to put together the IECC, and we'll talk a lot about that, that's the International Energy Conservation Code. The first thing they did was assemble a pretty large group of stakeholders, ranging from industry professionals and builders, building scientists, product manufacturers, but basically as large a group as they could possibly manage to discuss, debate, and masticate on what the codes were. And what happens is that in code development, it's a pretty long, painstaking process. And I can tell you, being involved in some public discussions on code meetings, you really get down into the nth detail, because with codes, they are going to become law, and they have to be very detailed, and then they have to be reviewed, and so it's a pretty lengthy process. The way that they address a lot of the building codes is that the ICC creates the code, the ICC administers the code, they do updates to these codes every 3 years. So as soon as a code gets completed, they almost immediately start taking comment on the things in the code that they'd like to have updated, changed. They have a public comment period of about 18 months. It takes a long time to get them done. Once the ICC finishes the codes, they get approved, but they're not necessarily adopted, and I'll talk a little bit more about that. It varies from state to state. The main code issues, the main documents that we're going to talk about in here, you saw all the other ones from plumbing, mechanical. We're going to talk primarily about the IECC, which is the International Energy Conservation Code, and how that applies to the built environment and what we're working on. And we'll talk about the ASHRAE 90.1 standard. And we'll go in greater depth on both of those in a few minutes. Mostly, energy codes apply to major components of the building: the envelope, the mechanical system, water heating, lighting, electrical power. And again, they set minimum requirements for all of those. We'll talk a little bit about some of those specific requirements. Quick chart, and this you do have to memorize. Just kind of the chronological development of all the current codes that we have. And really the biggest part of this is, if you can see, kind of right in that area, 1998 was when the IECC was formalized. put into play, and it became an amendment to the code, and really started, probably, I think at that point was really the big start of our second wave of energy conservation in the United States. So, again, the two that we're going to talk about, International Energy Code, it's a model code. It applies to residential, commercial, and it's written in mandatory enforceable language. And then the ASHRAE Standard 90.1, and it's a separate, let's see, ASHRAE, there's so many acronyms I can never remember all of them. American Society of Heating, somebody tell me if you know this, you can get a bonus point. Heating, refrigeration, I can't remember what the acronym is, but Energy Standard. And the reason they have two standards, the IECC was, again, written by the International Codes Council. It's a far more general document. It does have a lot of the minimum mandatories, and it's easy to integrate right into code. The ASHRAE standard, why we have a separate standard and what it does, and I'll go through in a little bit more detail, but it's a far more complex standard, and you'll find that both of these are applicable and both of these are acceptable for code approval, but ASHRAE is used primarily for larger commercial buildings. It's got a lot more flexibility in it for large system designs and space-to-space lighting design, and we'll touch base on that a little bit too. So they're both used, and again, ASHRAE is mostly for commercial and high-rise multifamily. And I'll talk about the energy budget approach in ASHRAE and how that actually does apply. But just for the purposes that for you to remember, the IECC, while it does apply and can be used for both residential and commercial buildings, the ASHRAE standard can make it easier for larger, more complex buildings to fit. As buildings get larger, there is not a one-size-fits-all system that works for them, and so allowing for energy trade-offs and allowing for flexibility and is why ASHRAE becomes a little bit more popular in larger buildings. And especially, and we'll talk a little bit more about it later, when you start to look at building energy modeling and some of the programs that are out there that are designed to be used early in the design process to start to estimate the amount of energy that a building is going to use, they integrate far better with ASHRAE than with the IECC. I briefly talked about code development process. I'm not going to spend much more time on this, but the development of a new code, it usually does take about 3 to 5 years, and then, as I said, it gets updated every 3 years. So it's a pretty lengthy process. The ASHRAE process is very much the same. They start with a consensus group or a working group or a committee. They come up with what they want as the baseline for the code and all of the specific code requirements. They put it out for public opinion so people can review it. All industry stakeholders can look at it. They take the comments, they make any substantive changes, come up with a final draft, and then it gets voted on for approval. So adoption of codes happens a couple different ways. In Montana, we do our code adoption by regulatory action. Department of Labor and Industry is responsible for all of the building codes, and they're the ones that decide which codes we're going to have statewide. Some states do it somewhat differently, and they have direct legislative action. And if you can go back to that list of all of those different codes, there's not just one code and then all of the mechanical and all the plumbing and all the energy. There's various different versions of them, and we'll go through that a little bit too. And in a lot of instances, some states are operating on different codes. We'll touch base on that. I don't want to get too far ahead. So again, this is kind of what I'm saying, that some states have their own legislative action. Others have, like Montana, we've got the Department of Labor and Industry Building Codes Department that approves the code. And then once the state approves the code, local jurisdictions have to switch and adopt to it. And usually there's about a 6-month to 12-month lag where the state will approve the code, and and currently they're looking at the most recent version of the International Energy Code, and it's likely the state will approve it, and then all the local jurisdictions that do building inspections will have to start following it. I just kind of touched on this already, and why they have an energy code and what they affect. In the energy code, there's minimum requirements for wall, floors, and ceilings, and it's minimum insulation levels. It's also a minimum air tightness, and we're going to spend a lot of time in the coming up in the next couple weeks, and talking a lot more about the physics of building and air movement, and how the tightness of the building can dramatically improve the energy efficiency. There's basic requirements for the doors and windows. They have to meet certain minimum energy requirements. And we'll talk a lot about that next week. I think you'll be talking about U value and U value and R value. And have you guys, I know you guys, we've been through it last class, but have you guys done anything yet on R values and U values? Very little. So we'll talk more about it, but basically R value is a resistance of a material to transfer heat. So the higher the R value, the more resistance, the better thermal properties a material has, and the code sets those minimum values. So they'll say that a wall has to be at least R21 or R19, depending on your climate zone. Minimum requirements for heating, ventilation, and cooling systems. So whether it's a furnace or a boiler system, however you heat the building, or your air conditioning, they have to meet a minimum federal efficiency standard. And again, we spent a fair amount of time on this last semester, but I don't know if you guys have ever seen a furnace or an air conditioner, and have you ever seen a little tag on it that might have an efficiency percentage on it? 90% efficient, 92% efficient. The code mandates the bare minimum for that, depending on which climate zone you're in. So for example, we have to use minimum 90% efficient heating equipment when it comes to forced air heating equipment. So you can't go get an older furnace and just throw it in, that might be 80% efficient, and just throw it in the house and call it good, because it's not going to meet the minimum code requirement. Lighting systems and equipment, and I'll go through some more specific stuff on ASHRAE in a little bit on that. But again, you have to use a minimum number of efficient light fixtures. And then your water heating system for your domestic hot water also has to be minimum efficiency levels. So aside from requiring minimum R values, minimum air change per hour in tightness of the house, and then the energy efficiency of your doors, windows, and your heating and cooling system, that's the primary target of the energy codes. And so it's the attempt to create the bare minimum, the least that you can do to create an energy efficient building. We'll spend a lot more time on this coming up when we talk about the systems approach and the whole house and the whole building approach. And one of the things is that, and especially as the energy codes get more stringent, and we're going to talk a little bit further today about some above code programs, it's very difficult to meet some of those requirements without looking at the whole building as a system. For example, if you think of it, the sports car analogy I've heard used pretty effectively, and so you can spend a lot of money on a car, and you can put an extremely powerful engine in it. It can be completely aerodynamic and streamlined. It can have the best suspension system in it, but if you put bald, crappy tires on it, you're going to end up in the ditch. And the same thing is true with the buildings that we're starting to build now, because minimum codes have ramped up significantly. And when we get into above code and we start to hit some things, and we'll talk about net zero and passive house, you can't just throw more insulation in the wall. It's not as simple as doing just one thing. You can't just put a higher efficiency furnace in it. You really do have to look at all of those things that the codes affect. The walls, ceilings, and floors, that thermal envelope, the heating system, the lighting, the design, and they all have to work together. So we'll spend a little bit more time on that, but the thing to remember is that it is really looking at the building as a system, and all the things work together and they work in concert. And you can't just improve one thing and effectively meet code, and you certainly can't just change one thing and effectively get a high performance building out of it. So we'll talk more about wall systems and different ways to comply with codes, and we're going to look at different wall systems and their performance. And this is when we start to do some of these energy calculations. We'll try different wall systems out and look at the performance of them, and you can see the difference between a 2x4 wall with fiberglass loose fill insulation versus a 2x6 wall with dense pack blown in cellulose with a much higher R value, much lower air infiltration. So we'll get to see some of those once we get further down the road. Just an example of some more building systems, and we'll talk a little bit more about them. So I guess one question, and with this integration of the classes here, I don't know how much you guys have worked on actually building and your understanding of wall systems. Anybody have any experience in construction? Do you understand how walls are built, and have you done anything in your other classes?
Not in other classes, just in
Life
life in general.
in general? Yeah. There's as many houses as you can see on the street. There's probably as many different ways that you can build a wall, and so we'll investigate a lot of different wall systems. And it really hasn't been until the last 10 or 15 years, and part of it's been code, part of it's been the green building movement, but we've been pretty set in building walls with studs, with a cavity in between the studs and throwing insulation in between them, and that's been good enough. We've made some significant changes in the last 15, 20 years, and we'll go through some of those, but the codes have helped. Getting energy codes in place, along with the structural, fire, safety, and basic indoor air quality codes, have definitely helped to ramp up the quality of what we put in our wall systems. But currently the codes just do minimum efficiency ratings for level of insulation in the walls, efficiency of your doors and windows. Codes do set basic criteria for your heating equipment, and not just the minimum requirements of it. We'll talk a little bit later about some of the ACA calculations, Manual J, Manual S, and Manual D, and they're designed to help determine what the actual heating load of a building is, and the codes set minimum standards for what that can be. So you can't, the whole purpose is designing a building that uses less energy. So the more they're putting into the codes, actual quantifiable requirements. And I guess that's one thing we talked about last semester that we didn't talk about in here. Well, we'll talk about it in green building systems, but the codes used to be very prescriptive, which meant there was a prescribed list of things that you could do, and if you did those things, you passed. It didn't matter whether those things gave you any improvements in your performance or not. If you prescribed to these practices, you met the codes. The codes are now moving into a much more performance base, and so you actually have to start quantifying your results. Before you can get a building permit, and we're going to do these, we're going to do res check calculations, you have to supply the basic wall systems, all your building materials, and minimum energy performances that your building's going to meet. And we're going to spend a whole day on res check, and you're going to do your own calculations for some simple houses. But you can't get a building permit now with the current IECC codes without demonstrating a model of performance for the building you're going to build. You can't just say, well, I'm going to use this much insulation and I'm going to use, you have to prove that it's going to meet that. It's not, until the 2015 IECC, it's not mandatory that you have to test the house, but it will be. So you understand the difference between those two, and that's a big movement in the codes, is moving from that prescriptive to the performance. And I would say in the next code cycle, probably by 2018, every single building that we build is going to have to be tested. Which are any of you guys doing the Saturn BPI certification? Are you guys doing that? Are you doing it? Are anybody interested in doing energy auditing and moving into that? I kind of thought it was going to be there 5 years ago, but I think we're a little behind. But I think 5 years from now it's going to be huge. Everything we build is going to need to be tested. And currently, I think we have about 2% of the people that we need on the ground to make that happen. So, if you're looking for a new career path, again, minimum lighting and electrical, we'll go through some of those and the ASHRAE, and then minimum for domestic hot water heating. So the basic process most of the time for the codes, and again, it varies from jurisdiction and local region. The minimum mandatory requirements, I don't know if you can see that, but the first thing you do is review the plans. So in order to get your building permit, you've got to do the calculation that the IECC uses is called a res check. We'll talk a little bit about that later. And so in that res check, you're listing out the materials and the products that you're going to use and the assemblies and how you're going to put them together. You're demonstrating a model of your energy performance, and then as the building gets built, you have to continue to comply with your inspections, visible air sealing inspections and insulation inspection to make sure that everything's done as per code, done as per your model. And currently it's not required. It will be in Missoula, I think starting October 1st. I'll double check that. But and then a blower door test to test for the air tightness of the house is actually required in some jurisdictions, and it will be required in all jurisdictions if they adopt the 2015 IECC. These are all the effective current codes that we have in place now. You don't need to memorize these. As far as the code compliance and adopting the new codes, Montana is usually pretty progressive. We were one of the first 4 states that adopted the 2012 IECC when it was developed. They've approved the IECC 2015. And I think there might be 6 states that are using the 2015 so far, and we're not far behind that. So the other thing I talked about was the ASHRAE standard. American Society of Heating, Refrigeration, and Air Conditioning Engineers. There you go. They were a trade organization originally founded just to, it says advance the arts and sciences of heating, ventilation, and air conditioning. Really, it was a group of manufacturers who were trying to update and upgrade performance. And they basically had become the foremost authority on heating, ventilation, and air conditioning. They've got 2 main standards that we use in building, and it's 90.1 and 90.2, which are the energy efficiency standards. The 90.2 is a residential for 4 stories or less, low-rise residential, and the 90.1 ASHRAE standard is for commercial buildings. And they are design guidelines specifically for energy performance, heating, and cooling systems, and for mechanical ventilation systems. And the ASHRAE 62.1 and 62.2 is for major ventilation systems and indoor air quality. The easiest way to kind of think of the two, if you're trying to separate them, 62 is for IEQ, and IEQ is indoor environmental quality, or you can say IAQ, indoor air quality, if that. So 62 is IAQ, and that's how you determine which one, if you were tested to. So they're basic standards. They're set to give guidelines for design and construction, operation and maintenance, and then utilization of renewable resources. And again, when I mentioned how we have to start looking at buildings as systems, the ASHRAE standards and also the codes look at these various sections of the building. So the envelope, the HVAC system, water heating, the overall power load, lighting and controls, and then any other equipment. So yeah, we'll get a lot more into the building envelope, but the standards set minimums for your assembly U factors, and this is the whole wall, including the amount of insulation and your windows and your doors. So it has to meet a minimum thermal efficiency, continuous air barrier, and again, we'll talk about conductive and convective heat loss, and so having an air barrier that keeps the air controlled in the house so it's not leaking out. Minimum calculations for all your heating systems. ASHRAE sets far more standards and has a lot more design standards and a lot more requirements, not just for your heating, your ventilation, and your air conditioning systems. And again, we talked about ASHRAE being far more applicable for larger commercial buildings. It also has calculations and specifications for all of the fans, pump controls, any motors, so anything that's going to consume even the smallest amount of energy. Lighting controls, and one of the things that we talked a little bit about in our first green building class, we've started to recognize now, we gotten pretty good at building a thermal envelope, and we can keep a lot of the heat inside the buildings. We've started to recognize that actually our electrical load is probably one of the biggest consumers of power now that we need to start controlling. So that's getting ramped up both in ASHRAE and in code. Again, I mentioned it's all based on climate zone. This is the Department of Energy listed climate zone. And I know that we've seen this before in Green Building 1. I don't know if you guys have seen this before, but it's designated as based on temperature and annual rainfall and humidity, different climate zones. And when we start talking about the physics of building science and heat transfer and moisture migration, where you live in the country can significantly impact your building differently. So the same building envelope that works here in Missoula, Montana might not be nearly as effective in Georgia. And next week, I think Brad's coming in next week to talk to you all about heat transfer and moisture migration and how those things impact the buildings that we build. But we have in Montana, we've got a pretty significant heating season, and we've got temperatures that can average maybe in the low 30s, high 20s with a relative humidity of about 10 to 15%. And so those conditions are going to impact our building envelope significantly different than if we're in the southeast and it's 96 degrees and we're running the air conditioner and the relative humidity outside is 85%. I see Kurt, he's all excited back there because he knows all about vapor drive, and he's so excited he can't keep his eyes open. All of these standards, both the codes and the ASHRAE standards, and all the programs we're going to touch on here after a bit, are all based on climate zone. Because obviously, again, one part of the country is going to have significantly different requirements when it comes to thermal envelope and U values of the windows and moisture control than the other. And we'll spend a bunch of time talking about that, but I don't want to, I've got an entire semester-long class on moisture migration and vapor drive, so I don't want to go down that wormhole right now. ASHRAE, again, just basic requirements, new buildings, additions, alterations. Very similar to exactly what's in the IECC, HVAC system, service water heating, a couple of different things, and this is why ASHRAE starts to become more important for larger commercial buildings, more complex spaces, is because it does have delineations for different types of space. You won't have to determine which space is which, but it differentiates between conditioned space, unconditioned space, and then semi-heated space, which for larger building design can sometimes significantly increase energy efficiency if it's properly used. But if it has to be treated exactly as the same conditioned space as the thermal envelope, it's going to far exceed the capacity of what the heating system might be. Don't worry about making those calculations as of yet. So again, minimum requirements for all of these things, all of the equipment for heating and cooling. I'll talk in a little bit about the ACA calculations, but ASHRAE also takes into account duct design. We got a lot of information in here. Low voltage dry type distribution transformers, which are the voltage reduction in larger buildings. We don't need to go into that. So again, ASHRAE, also general lighting scope, lighting inside and out of the building. They're all requirements. Basic inspection items, and this is the same for, pretty much the same for the IECC. The wall insulation after it's installed, any roof ceiling insulation, all of the windows and the window insulation, the air barrier, and so all those things are thermal envelope requirements, and both the IECC and ASHRAE have specific inspection requirements for those. Again, the codes are moving far away from basic prescriptive, so you can't just check off on a box and say, yeah, we put the wall insulation in, and yeah, we put the air barrier in. It actually has to get physically inspected. Mechanical systems and equipment, we'll talk a lot about performance testing and building commissioning, but moving into as part of code now, again, it's one thing to say we're going to use a system that's rated at this efficiency, but it's far more important to have it tested after it's installed to make sure that it's operating properly. And so that's becoming part of codes and requirements. We'll get into a lot of the air ventilation requirements, and we don't need to go into that today. So the 62.2, the minimum ventilation requirements, are also becoming a big part of both residential and commercial codes. And the biggest reason for this, and we'll talk a lot more about it, is that as we start to make buildings tighter and tighter, we get less fresh air into them. And so ventilation becomes a big issue. It's a big issue both for occupant safety and health, so that the air that they're breathing doesn't have a high level of toxicity and volatile organic compounds in it. It's also a big issue for the moisture migration and the moisture drive that I was talking about. One of the biggest challenges, and we don't see it so much in our climate zone, but any other climate zone that's got a significant amount of moisture in it, mold growth inside the walls is becoming probably one of the biggest and most heavily litigated building envelope failures in the country. And it comes from lack of ventilation, lack of proper installation of air barriers and vapor barriers. So we'll go more into that, but this is just a chart that shows you the basic, you can't see my cursor, basic minimum ventilation requirements. And again, these are minimums, they're codes, they're just enough to not break the law, so they may not necessarily be the most recommended. But it's just a chart that shows you based on square footage, airflow in cubic feet per minute, how much fresh air you need to be bringing in the home. We'll go through these calculations a little bit when we go through conductive heat loss and minimum ventilation guidelines. But based on how tight the home is, you can come up with a recommended minimum ventilation. So don't worry about this yet, but we'll go through that and you'll be able to do that calculation. When we do our res check on our sample house, we're then going to play with that a little bit and come up with a couple different building envelopes, and some are going to be tighter than others. And the tighter the building envelope, the more mechanical ventilation we're going to need. Just know that it's all set in code. Also sets both there's several minimum requirements in the IECC. ASHRAE is a little bit more specific in what it requires for spot ventilation in kitchens and bathrooms. But again, just making sure that we're getting rid of excess moisture, not having stale air in the house. We'll talk about different ventilation systems, but one of the other challenges and what's set into the ASHRAE standard three basic types of ventilation. You can have exhaust-only ventilation, supply-only, and balanced. So with exhaust-only ventilation, like a bath fan or a kitchen range hood, all you're doing is taking air from inside of the house and venting it out. And the inverse of that, supply-only ventilation, is if you've got a fresh air vent and you're just sucking air in. They both have effective purposes, but for thermal performance, if you start pumping air out of a house and you're not bringing any extra air in to balance that out, you're creating a negative pressure system. And so air is going to come in somewhere, and when you create that negative pressure system, it comes in wherever you have a gap or a hole or a crack, and so you're not controlling it. So you're losing your thermal performance on it. So we'll talk about basically what ASHRAE sets up is if you have X amount of exhaust-only ventilation, then you have to bring a minimum amount of fresh air in, and inversely, if you're bringing in X amount of fresh air, you have to exhaust this much amount of air. Anybody ever been in a house where the heating system kicks on and one of the doors slams shut? Or it's because it's a situation where you've got too much air moving. You create a positive or negative pressure situation in one room or the other. And so basically that's what the ventilation requirement is. Don't worry about getting into run times and some other minimum stuff, and these are more building science things. Kitchen range hoods, dryers, bath vents, they all have to be vented to the outside. Believe it or not, until these minimum codes came in place, a lot of people just vented all of their stuff right into the attic. So that warm, moist air that's coming out of the bathroom, jetting right up into the cold attic. We'll talk a lot more about that, but do you guys know what happens when warm, moist air hits something cold? The vapor in that, it reaches a dew point, the vapor in that turns to bulk moisture. So, yeah, major water damage issues with vented appliances that don't vent to the outside. I mentioned these briefly, and these are also part of what code and some of the above code requirements rely on. The Air Conditioning Contractors of America is another industry organization that puts out standards. The three primary standards that we rely on are the Manual J, the Manual S, and the Manual D. And the first one, the Manual J, we'll do a simplified version of Manual J calculations to get our design load of our sample house when we get further down the road. But what the Manual J calculation does is, based on those inputs, the materials you're using, the R value, the overall U value of the walls, the air infiltration rate, it gives you a design load of how much heating or cooling that building's going to need. So it tells you, based on the input that you have, this building is going to use 18,500 BTUs per hour. And it's extremely useful because it starts the process of trying to model a building. If you're looking at hitting energy performance targets, it gives you that baseline. So, for example, you can do your calculations, you can get your design load, and you may hit your design load and it's 18,500 BTUs per hour, but to hit the energy goals that you've set for your project, you can't have more than 12,500 BTUs per hour. So you've got to go back and look at your thermal envelope, you've got to look at your other building systems, and you figure that out, you get your total load through the Manual J, the ACA Manual J. The second part of it is the Manual S, and once you have that design load, you know your building is, the volume of your building is X cubic feet, you have 12,500 BTU per hour as your average load. it can give you the size, you can use that to select the size system that you need. And you would find that using the manual S. And then the last part of it is the manual D, and just for forced air systems, but residential duct design. And again, we did spend a fair amount of time talking about this, so I'll go through it really quickly. You take the energy and the effort to get accurate load calculations so you know how much energy your building is going to need, and you get that through the manual J. Then you use the manual S to select the proper equipment. You have to deliver that, and you have to deliver it efficiently, or those two numbers aren't going to mean anything. And so that's what the manual D is the residential duct design system. And so based on the length of your heating runs, it tells you how big they need to be. Every time you put a corner into a air delivery duct, it slows down the velocity of the air. And so based on that calculation, if you have a heating system over here and you need to deliver air 5 rooms down and you need to get 40 cubic feet per minute out of that register, the manual D will lay out that duct design for you so you can actually get that design load out the other side. Make sense? So let's take a quick break right here. And we spend a lot of time talking about the codes before we get into the above code stuff, because the great majority of the energy performance in the green building programs and some of the above code programs that we have are all based on the code. And so very simply, in a lot of them, they will say must be X% better than current code. So strictly on performance standards, the code sets the minimum floor, and then some of these above code programs just really specify how much more above and beyond you need to be from that. So, any questions on that part of it, the basic codes? Take a quick break, maybe about 10 minutes, and then we'll get back and go through briefly some of the above code stuff, and some of the energy requirements of a few of the green building programs. And again, the whole point of what we're talking about is there really is there's no one thing that's going to say this is an energy efficient building. And no matter where you are, whether you're talking to building owners, architects, commissioning agents, engineers, builders, the realm of what constitutes energy efficiency ranges from the very simple, and I can tell you that some people believe that even the codes are too stringent and our energy requirements should be less than that, to the far extreme where some people believe a building's not energy efficient unless it's generating more energy than it's using. So, take a break. We'll get back to it in a